There's a black hole racing through intergalactic space right now, and it's not supposed to be there. Supermassive black holes don't leave home. They anchor themselves at the center of a galaxy for the rest of cosmic time, sitting at the bottom of gravitational wells, too deep for almost anything to escape. That's the rule. It's held for as long as we've been studying them. This one broke it. Something threw it clear out of its own galaxy, and it's now tearing across 200,000 light years of empty space at nearly 1,000 kilometers a second, dragging a trail of brand new stars behind it. Millions of them. Newborn, blue, still hot from formation. Here's the part that breaks the picture we all grew up with. Black holes are supposed to be the end of the story. They devour, they destroy. Stars fall in and nothing comes back out. So why is this one leaving new ones behind? And what in the universe has enough force to grab something with the mass of 10 million suns and throw it out of its own galaxy like a stone from a slingshot? I'm John, and this is Deep Space Report. Today, we're tracing this discovery from the beginning, the moment astronomers first spotted an unexplained streak of light, through every failed explanation that came before the real one, to the violent cosmic event that sent a supermassive black hole flying. By the end, you'll understand not just what happened, but why scientists think it might be happening far more often than anyone ever suspected. Every great discovery in astronomy starts the same way, with something that shouldn't be there. In 2023, a team of astronomers working with the Hubble Space Telescope was studying a small, unremarkable dwarf galaxy, the kind of target that fills in gaps in a survey rather than making headlines. Hubble has spent decades doing exactly this kind of quiet, patient work, cataloging galaxies, mapping black holes, photographing nebulae so beautiful they end up on classroom posters. It's not usually where the strangest discoveries happen, but this time, something in the data refused to make sense. Running alongside the dwarf galaxy was a narrow, impossibly straight line of stars, young, blue, and hot, stretching nearly twice the length of our own galaxy and carrying the combined mass of 100 million suns. The astronomer who found it, a team led by Yale's Peter Van Dockum, didn't hedge. He said plainly that nothing like it had ever been observed anywhere in the universe. That's not a sentence astronomers use lightly. So the team did what scientists do when the universe hands them a mystery. They started ruling things out. Could it be a galaxy? A very thin, very unlucky galaxy, seen exactly edge on, so that all we're seeing is its narrow profile? It's a reasonable first guess. Except a real galaxy is a mixed population. Old stars and young stars, red and blue, all ages tangled together over billions of years. This streak wasn't like that. Every star in it was young. Every star was blue. And the leading edge was glowing with something called doubly ionized oxygen, a signature that only shows up in the most violent, high-energy environments imaginable. You don't get that from an ordinary galaxy quietly rotating in space. Explanation 1. Eliminated. But if it wasn't a galaxy, what was throwing off enough energy to draw a line across the cosmos? Could it be triggered? Star formation from a nearby galaxy's jet? This isn't far-fetched. Astronomers have seen it happen before, most famously in an object called Minkowski's object, where a jet of radiation from a black hole slammed into a cloud of gas and lit it up with new stars. If that were happening here, the pattern should be obvious. The jet would be widest and most powerful close to its source, and it would taper as it traveled outward, losing energy the farther it got. This streak did the exact opposite. It was narrowest, almost a point, at the tip farthest from the galaxy and widest close to home, backwards. Whatever was making this line, it wasn't a fading jet. Explanation 2. Eliminated, which left the team with an idea so strange that even raising it felt like a stretch. A runaway black hole. Think about what that phrase actually demands. Not a black hole quietly sitting at the center of a galaxy, doing what black holes are supposed to do. A black hole in motion, moving fast enough and far enough to physically outrun the gravity of an entire galaxy behind it. Nothing about that is a small ask. Escaping a galaxy's gravitational pull takes real. Staggering velocity and supermassive black holes are not exactly known for being easy to move. They sit at the bottom of the deepest gravitational wells in the universe. Whatever could throw one clear would have to be one of the most violent events physics allows. Here's the thing about runaway black holes. Until very recently, they were pure theory. Chalkboard physics. Yes, technically answer with no evidence behind it. Back in 1983, a physicist named Michael Fitchett worked out the math showing that when two black holes collide and merge, the collision doesn't always happen symmetrically. If the merger is lopsided enough, it releases gravitational waves unevenly in one direction, and by the same law that makes a rocket move forward by pushing exhaust backward, the newly merged black hole gets kicked in the opposite direction. Hard. Hard enough, in theory, to send it flying out of its home galaxy entirely. It was elegant. It was mathematically sound. And for 40 years, nobody had ever actually seen it happen. The problem is obvious once you think about it. How do you spot a black hole in the act of fleeing a galaxy? Black holes don't glow, they don't announce themselves. Unless one happens to leave behind an enormous, unmistakable calling card, like, say, a 200,000 light-year trail of freshly minted stars, you'd never know it was there at all, which is exactly why this streak mattered so much. The confirmation didn't come easily, and it didn't come quickly. It took years, better instruments, and a second, far more powerful look. In December of 2025, Van Dokkum's team returned to the streak, this time with the James Webb Space Telescope, an instrument built to see exactly the kind of faint, distant detail that Hubble could only hint at. What they found settled the question. At the very tip of the streak, JWST detected an enormous bow shock, a wall of superheated, compressed gas, the same kind of shockwave you'd see piling up in front of a supersonic jet, or water bunching up in front of a speedboat's hull. Something massive was plowing through the space in front of it, compressing everything in its path. And the numbers behind that, something were staggering. An object at least 10 million times the mass of our sun, moving at roughly 954 kilometers per second, fast enough to escape a galaxy's gravity entirely, fast enough to escape the faint halo of gas that surrounds every galaxy like an atmosphere. Fast enough, in other words, to actually be gone for good. 2 more pieces of evidence sealed it. Emission lines confirmed compressed, superheated gas at the tip. A sudden jump in velocity confirmed something was moving through space far faster than sound could travel through it. Every piece of evidence pointed to the same conclusion. This was the wake of a runaway supermassive black hole. They gave it a name, not a poetic one. Scientists rarely bother with poetry at this stage. They called it Runaway Black Hole 1, RBH1. For the first time in the history of astronomy, here was confirmed photographic evidence of a supermassive black hole fleeing its galaxy. So RBH1 is real. Confirmed, photographed, and it still doesn't make sense. We think of black holes as endings. They're the villains of astrophysics, the objects that swallow stars, strip apart solar systems, and let nothing escape, not even light. That reputation is earned. It's accurate. How, then, is this one building stars? The answer turns out to be almost poetic in its mechanics. As RBH1 tears through space, its bow shock doesn't just compress gas, and it disturbs it, heats it, and leaves it churning in its wake. As that disturbed gas cools and drifts back together, gravity does what gravity always does. It pulls clumps of matter inward until they're dense enough to ignite. New stars, born directly from the wreckage of the black hole's passage. It is, quite literally, destruction seeding creation. The very chaos that should be RBH1's calling card as a monster is the same chaos laying down the raw material for 100 million new suns. From cosmic carnage, stellar rebirth. But that answer only opens the next question, the one that had been sitting underneath everything from the start. Where did RBH1 come from? What could possibly throw an object with the mass of 10 million suns out of a galaxy at nearly 1,000 kilometers a second? The trail didn't just point forward toward where RBH1 was going. It pointed backward, too, straight to where it came from. Follow the streak to its oldest end, and you arrive at a galaxy system roughly 7.5 to 9 billion light years away. Astronomers gave it a name as soon as they saw it because its shape was too strange to ignore. 2 glowing ring-shaped structures side by side, with a bright connecting bridge between them, forming what looks unmistakably like a pair of wide eyes and a beak. They call it the cosmic owl. Some call it the infinity galaxy. And its shape isn't decorative. It's a record of an almost unbelievably rare event. Ring galaxies like this only form one way, when one galaxy passes almost dead center through another, punching straight through its core like a dart hitting a bullseye. Think about how difficult that actually is. Even with a steady hand, most darts land somewhere off-center. Galaxies don't aim at all. They drift through space along whatever path gravity happens to set them on. A direct, centered hit is astronomically unlikely. Ring galaxies make up roughly 1/100% of every galaxy we've ever cataloged. Only a few hundred are known to exist nearby. So, what were the odds that 2 of them would find each other? Now stack the odds. Not 1 rare ring galaxy, 2 sitting close enough to interact, and not just close, colliding head-on, with enough symmetry that both galaxies had to be roughly the same mass to produce the balanced, owl-like shape we see today. That's not just a coincidence, that's one of the rarest events the universe has ever recorded. Roughly 38 million years ago, the leading edges of these 2 galaxies, and the eyes of the owl, began to merge. Where they met, in the region astronomers call the beak, gas piled up, compressed and ignited into a dense, active site of star formation. It's a scene of pure cosmic violence. And it's also, most likely, the exact place and moment that set RBH1 on its escape trajectory. Each ring galaxy on its own is modest by cosmic standards, roughly a quarter the diameter of the Milky Way. But at the moment of collision, Each one still carried its own dense core of ancient stars, wrapped tightly around its own central black hole. Two separate cores, two separate black holes, crashing together almost perfectly head-on. Astronomers can tell it was close to a direct hit because of how symmetrical the resulting owl shape turned out to be. An off-center, glancing collision would have smeared the rings into something lopsided and messy. Instead, we got two clean, matching eyes. That symmetry is a signature, and it tells us the two galaxies that collided were close to the same mass, hitting each other almost exactly along the same line. At the center of each of those two colliding galaxies sat a supermassive black hole, surrounded by dense, ancient cores of old stars. When the galaxies merged, those two black holes didn't stay apart. Drawn together by their own overwhelming gravity, they spiraled inward, closer and closer, orbiting each other faster and faster until they finally collided and merged into one. There were two competing theories for what happened next. One possibility, a three-body interaction, where the two central black holes formed a long-lived binary pair, something that can persist for billions of years, and then a third black hole wandered close enough to disturb the system, flinging one member of the pair out into intergalactic space. This was actually the leading theory back in 2023, before JWST weighed in. Or a direct merger. Two black holes spiraling together, colliding, and releasing gravitational waves so violently and so asymmetrically that the newly merged black hole recoiled, like a cannon kicking backward when it fires, hard enough to escape the galaxy entirely. So which was it? A shove from a bystander or a direct hit? Telling these two scenarios apart isn't easy from a distance of billions of light years. Both involve black holes ending up somewhere they shouldn't be. Both involve enormous velocities. Both would leave behind a wake of disturbed, star-forming gas. The difference lives almost entirely in one number. Everything came down to mass. If a three-body interaction had ejected a black hole, physics says it should be the smallest of the three that gets thrown clear. The lightweight one, bullied out by the two heavier ones. But RBH1 isn't a lightweight. It's enormous. North of 10 million solar masses. Too massive to be the leftover runt of a three-body fight. Exactly the size you'd expect, though, if it were the freshly merged product of two roughly equal black holes, kicked out by the recoil of their own collision. Mass was the smoking gun. The math only worked one way, a merger and a gravitational recoil so powerful it hurled a black hole clear across a galaxy, through its halo of surrounding gas, and out into the empty dark between galaxies, never to return. Somewhere behind it, the merger may have left the cosmic owl's core temporarily without a central black hole at all, a wound at the heart of a galaxy that took nearly 40 million years to make and will take far longer to heal, if it ever does. Here's where this stops being a single strange story and starts being something much bigger. Galaxy mergers are not rare events in the history of the universe. They are, if anything, routine, the normal expected outcome of gravity acting over billions of years, which means black hole binaries should be forming constantly, which means mergers, and the violent recoils that follow them, should be happening far more often than we've ever managed to observe. We were only able to see this one because it left behind an almost impossibly large, almost impossibly lucky calling card. A 200,000 light-year trail of glowing new stars pointed directly at Earth's line of sight, bright enough for our best instruments to catch. Most runaway black holes wouldn't be so generous. So if this one nearly slipped past us, how many others already have? And in fact, we may already be looking at some of them without knowing for certain. Astronomers have flagged other candidates worth watching. A spiraled galaxy called JUR 43724056, roughly 288 million light-years away, whose central black hole appears to be drifting at a noticeably different velocity than the rest of its galaxy, and a galaxy cluster called Abell 2261, whose core should be home to one of the largest black holes ever measured, somewhere between 3 and 100 billion solar masses, except when astronomers look for it, the black hole simply isn't where it should be. Missing. Possibly, just possibly, kicked out the same way RBH1 was. None of these are confirmed the way RBH1 is. They're candidates, question marks, open threads. But that's exactly the point. For decades, the runaway black hole was a theory with zero confirmed examples. Now it has one, and the search for the next one is already underway, aided by wide-field surveys from missions like Euclid and the upcoming Nancy Grace Roman Space Telescope, and increasingly by machine learning tools built specifically to catch these faint, thin streaks before human eyes ever would. We may be standing at the very beginning of an entirely new category of object in astronomy. Not a handful of oddities, but a whole hidden population of wandering black holes, quietly crossing the dark space between galaxies, invisible until one of them happens to leave a trail bright enough to notice. It's worth sitting with how recently all of this became possible. For most of the history of astronomy, a claim like supermassive black holes can be ejected from their galaxies would have lived entirely in the realm of theoretical papers and simulations. Numbers on a page, plausible but unproven. It took an unusually favorable alignment of circumstances to change that. A black hole massive enough to leave an unmistakable wake, moving in a direction that happened to point its trail toward Earth through a stretch of space clear enough for our telescopes to resolve it, discovered by a team paying close enough attention to notice a straight line where nothing straight should exist. Change almost any one of those variables, and RBH1 might still be theoretical today. That's a sobering thought. It suggests that for every runaway black hole we're lucky enough to catch in the act, there could be dozens or hundreds moving through the dark in directions and configurations we simply aren't positioned to see. For a long time, we treated black holes as fixtures, permanent residents anchored at the centers of their galaxies for the rest of cosmic time. RBH1 proves that isn't always true. Sometimes the most extreme collision in a galaxy's history doesn't end with something being destroyed and left behind. It ends with something being thrown clear across the universe entirely, carrying its own violent history with it, and leaving behind a glowing trail as proof that it was ever there at all. And maybe that's the strangest part of this whole story. The very thing that makes RBH1 terrifying, its raw, uncontrollable violence, is the exact same thing that gave 100 million new stars the chance to exist. Destruction and creation running along the same 200,000 light-year line, inseparable from each other. Somewhere out there, right now, it's still moving, still compressing gas ahead of it, still leaving new stars glowing quietly in its wake. A black hole that was kicked out of its home and is building a new one, star by star, as it goes. If you want to keep up with discoveries like this one as they happen, our weekly newsletter breaks down the biggest stories in space in a few short minutes. No fluff, just the good stuff. Links in the description. Until next time, I'm John. Stay curious.